nanohub.org.
You can follow along with this presentation using printed slides from the NanoHub. Visit www.nanohub.org and download the PDF file containing the slides for this presentation. Print them out and turn each page when you hear the following sound. Enjoy the show.
Okay, we'll get started and let others drift in, or diffuse in, should I say. Okay, this is lecture 18 on continuity equation, and today we will finish essentially the development of the transport equation, and for the first time we'll solve a few concrete problems. Now, in some way you should realize that until 1950, early 1950s, this was the state of art of understanding. In fact, for last 50 years, most people have essentially just solved these equations for variety of context. And only recently, about 10 years or so ago, that things have, 10 or 15 years, the things have began to change in some respect here. That we'll discuss perhaps later on. So we'll talk about continuity equation, then we'll solve an example problem, and then we will conclude. Now, as I have mentioned several times before, that there are these 5 equations. In fact, 3 equations, if you count properly, that is in the first equation, which is the continuity equation for electrons, and I'll explain why, what do I mean by continuity. Then you can see that there is an expression for the current, and the second equation simply says how the current responds to electric field and density gradient. So you put the second in the first one. In fact, those two are one equation. And similarly, there are another continuity equation for the holes, and finally, the Poisson equation. Now, we will talk about the first and the third equation today. Now, before I move on there in talking about and discussing this, let me point out something important. If you looked at the 5th equation, this is called a Poisson equation. Now, Poisson equation relates the charge to the electric field, or here the displacement is d related to the electric field with dielectric constant multiplied by the electric field. Now, when devices become very small, molecular devices or so, not transistors, big transistors that we talk about, this equation, the Poisson equation, might get modified. In fact, it does get modified, because in any of these, the electron-electron interaction, very close electron-electron repulsion, is not accounted for. Here, as if one electron is moving, and the rest of the electron is sort of in a background, or the combination of protons and electrons is moving in response to that. So this equation on more sophisticated physics and smaller devices might get changed, but for most devices it's pretty good. Similarly, the second and the 4th equation, which combines drift and diffusion, when you have very small device in which you do not have any scattering for electrons going from one contact to the other, then in that case, these 2 equations will also not be correct. These equations are valid when you have a lot of scattering as you're going from one contact to the another. So therefore, in many recent results, if you see in the literature, you will see that there are modifications for the expressions for the current Jn and Jp when the scattering is not as strong, and diffusion-Einstein relation may not be valid within the device. But the first and the third equations, these are conservation equations, valid always, regardless of what detailed physics you put in for Jn and Jp. It's valid always, and let me explain why. Because this is simply conservation law. So long electrons are neither created nor destroyed in a global sense, then of course these relationships will hold. So let's consider a semiconductor of an arbitrary shape, shown here on the right, a top view, and the ash color region is, let's say, top view of a semiconductor, and I have put 2 contacts there, square-shaped contacts, and if you apply a voltage, then the current will flow from one contact to the other. Now assume that I have divided this region into many minuscule squares, or in 3 dimension you can say many minuscule cubes of size A. Now this size is not, of course, atomic size A. I'm talking about more like, let's say, 15 to 30 angstrom, a relatively big region, almost macroscopic in terms of properties. Effective mass is valid, mobility is valid, those concepts are valid, but smaller compared to the device dimension. In that case, if you put some boxes in, the green box, the green and blue and the yellow, you will see the electrons sort of streaming in to the box, let's say the blue box, and gradually streaming out of the box. So say there is a certain number of electrons which will get in and certain number of electrons which will get out. So let's blow that region up and look at this 3-dimensional picture, sort of, looks nice, and in which the electron is coming in and getting out. So I will consider that box to be of size delta x. The length of the box, blue box in the middle, let's call that delta x. And let's call the effective area A equals 1. You know, A can be any number, this is the width and the depth, but we'll call it 1 in some units. Now, if I counted the number of electrons that are coming in and out of this, then you can say that, let's say, the certain number of electrons coming in Jx. Now, in 3D, it will be a component of x, y, and z. I'm thinking 1 dimension for this simplicity here. And there's certain number of flux, certain number of electrons per second that is flowing in the box, and certain number of electrons flowing out of the box. Now, how many? How would you do the bookkeeping? Well, you can write something like this. On the left-hand side, what I have of this equation, what I have written, that how the number of electrons within the box change with time. Do you see? Let's say n is the number density, right? Number per centimeter cube. And if I multiply it by the A, which is the cross-sectional area, and delta x, which is the length of that box, that's the volume. So that's how many electrons I have within that little box. Now, how does it relate to the current? Well, that depends on whether the number is growing or coming down, depends on how many is coming in and how many is getting out. Just like in this room. Let's say students are constantly flowing in and some of them are leaving. So the number growth within the room will depend on the flux of electrons coming in and the flux of electrons getting out. Now I have divided it with minus q in the denominator because these are electrons and I want the number. And so in the J sub n, there is already a minus q. Remember that this is because it's electron current density. Okay, so this is almost done. If I didn't have any other process, in fact, this would be the equation that will tell me how many electrons are coming in and out. Now remember, this J sub n are the fluxes that are coming from the contact, sort of, right? These are drift and diffusion current. But of course, there are another current that we can also think of, that if you shine light, that's a third contact from which electrons, holes can come from, right? So in that case, assume that the top yellow one, arrow downward, it is as if light shining on that sample. So electron not coming from the contact, but coming from outside. And that one, and similarly, I can have a recombination. Recombination of these electrons. Recombination to what? Recombination to the holes. So in that case, the electron is not getting out of the device. For the top one, the generation, photon is coming outside and in, but we'll talk about that in a second. So G sub n and R sub n represents electron generation and electron recombination through trapezoid tunnel, trapezoid recombination or direct recombination, that type of thing. And so all you have to do is again multiply with the volume and the Gn, because Gn, what is that? That's the number per centimeter squared per second, per centimeter cube per second. So that's the generation rate and correspondingly the recombination rate. You can see A is the same everywhere, so you can just divide it out. And once you divide it out, you see only place there will be a delta x left. Why do you see that? In the first term on the right hand equation. Everywhere else, the volume got uniformly multiplied, so everything has lost all this A and delta x in this process. Now, this derivative, Jn at x and Jn x plus delta x divided by delta x. What is that? That's the definition for derivative, right? That's the normal definition for derivative. And so in general, if you think about three dimension, you will call that a divergence. Divergence is how many particles going outward. So if you think about it, there's a minus q down there in the second part or first term on the right hand side. If you put it in, you will see the first term actually represents the number of net outflow of electrons. That's divergence. And so that's what I have written on the right hand side. Okay. Now you see in this equation it is saying that the electron number within a particular box can stay flat. You know, somehow all the fluxes that are coming in, they balance each other. It can stay flat. Electron number can go up. So how come electron is not being created or destroyed? Well, the reason electron is not creating and destroyed is in the global material, and I'll explain that in the next slide. But within this one equation, electron number can go up, it can go down as a function of time, it can change as a function of distance and within the volume. No problem, that can happen. But still, in the next slide, I will show that the net number, the total global number, that doesn't change. So you will have one equation for electron, you can write that, that's easy. And similarly, you will have another equation for the holes. Now, this hole, G sub P, and you realize G sub N for the electron, this is the same flux actually, because the same photon came in and generated electron hole pairs. And so Gn and G sub P, these are generally the same. There are special cases where it can be different, but in this case, we'll assume it's the same. And similarly, the Rn and R sub P, this is the rate at which electrons disappear. The holes must disappear at the same rate because it's recombining with the holes. So therefore, these two processes are actually coupled. And correspondingly, you will have a equation for the holes. Only thing that is different in the second equation is, do you see this? There is a negative sign in the first equation. And why there is a negative sign? Because holes carry a positive q. So when you write the equation, on the denominator you will write a plus q. And once you do everything else, because of that plus q in that term, you will have a correspondingly negative of the divergence. That's it. And so therefore, these two equations will be globally linked. Now, the continuity equation in general, as I said, I want to re-emphasize this, that this generation process, G sub N, is always actually equal to G sub P. Because anytime you generate an electron, pump it up by photons, let's say, you leave behind one hole. So the number of electrons that is increasing is the same as number of holes that is increasing, right? And similarly, the recombination process, well, they recombine with each other and therefore they get lost at the same way. Right? Now, so now one thing you should look that if I were to actually take a difference of this or sum them up, dn dt and dp dt, you should convince yourself that net rate should be independent of the current that is flowing in, because no net number of electrons can change. Holes have been created, that means electrons have been pumped up, but that does not change the total number of electrons. When something got recombined, an electron was in the conduction band that came down to the valence band. But if you look at the material as a whole, of course, electron and hole remains the same, no problem. Individual component can change easily, electron and hole number, but not the global number. See, it's a very important thing to remember. An analogy, since we are at Purdue, we must have a Wabash River around, and let's say this is some sort of lake for around that place where, so the first term will be the rate of increase in the water level in the lake. That is that little cubic box, which is like a lake here. That must be equal to the inflow and outflow. The deep blue regions, these are electrons coming in and electrons getting out, or water particles getting in and water particles getting out. Rain is coming sort of, this is generation rate. And then the evaporation getting out is sort of the recombination rate. So the reason I wanted to say that this is global, this is sort of a very general law. This, you see here, there's nothing about electrons or holes. Anytime you have a bunch of particles, you can write a global continuity equation that really doesn't matter whether you know about quantum mechanics, statistical mechanics, doesn't matter. The physics comes in one level below when you want to write equations for the inflow, when you want to write for equations for the outflow, and then like the evaporation, the physics of evaporation will determine the rate, right? The pressure difference and everything. The physics will come in filling up individual terms. But this equation as a whole, this could have been written 2,000 years ago, and it would still be fine. You don't need any quantum mechanics or any sophisticated thing before that, right? Okay, so that's the equation, general terms. Remember that you should always be able to write these equations. If I put 3 contacts in here, you should be able to write this equation regardless of how many contacts I put, regardless of whether you know the physics of the problem or not. Okay, so all the equations are in place. We are in good shape. We know drift and diffusion equations. We know the continuity equation we just derived. Now, if you have to solve it, now there will be a problem. Do you see why there might be a problem? First of all, how many unknowns do I have here, do you think? I have 3 unknowns. Do you see? Electron number, hole number, and the electric field or potential. How so? Isn't there a recombination rate present there, R sub n or R sub p? Well, yes, but remember, in Shockley-Rittal recombination, I will replace that term as np minus ni squared divided by the big denominator. So that term inside it actually only has n and p. So I can forget about that. Generation rate, most of the time it's a certain flux, certain number that will be given. Let's say cosmic ray is hitting your device. It will generate a certain electron hole pair. So that will be a given number. And you can see that mu n and d sub n, these are constants, right? These are constants. So I have 3 partial differential equations. Now that's not an easy problem to solve, and most of the time you'll need a big computer to solve it. But remember, most of these problems were solved 50 years ago, before computers were widespread. The use of computer was widespread. So how did they do that? Well, they used a lot of approximation. Now, one thing before I go on, I want to mention this, that many times people equate approximation with a negative connotation. Oh, he has approximated the problem. I want to flip the thing around. I say the people who can do approximation correctly may know physics better than most people, because they can identify what 10% of the problem or issues govern 90% of the problem, right? So being able to identify that 10% requires understanding more physics, not less. So what I'm going to do as I show you how to make approximations, and this has been done by great people. You know, many of them things are copied from the days of Shockley and others. So these are actually very great people, many Nobel Prizes. They have made these approximations. So you can understand that why these have deep physical insight. But you have to understand also what did they do, and in that process, develop your own intuition. It will take a little bit, but you will be able to do that if you follow the logic. So there will be 2 methods of solution. One is numerical. These days, there are very sophisticated simulators. You go to NanoHub and you will be doing that. You can solve the problem. And that's numerical solution. I will show you a little bit, just like I showed you how to do Schrodinger equation, right? Discretization and other. I will show you how to do that. But today, we'll be talking about the analytical method of how to solve it easily. So generally, eventually, the analytical solutions, the solution of the Poisson equation will be given by a graphical solution. And the graphical solution of the Poisson equation is called a band diagram, and we'll see how to draw it. Now, one important point is that if you don't learn how to do band diagram in this course, you will never learn it, and actually, you have wasted your time in this course. The single most important thing that I can say for this course and also for the exams is that you must learn band diagram, how to draw band diagram, and I'll show you step by step how to do that. And then, of course, we'll be solving it in various approximations, these 4 equations in diffusion approximation, minority carrier transport, ambipolar transport, on wide variety of approximations we'll be solving that complicated equations. But the good thing about these approximations are that they are so simple, you can then eventually solve it in 3 lines. But of course, you shouldn't approximate yourself out of the problem, because then you'll not get anything. So let me show you one example. So consider that I have a crystal, and this blue, and as the crystal is growing, I'm incorporating a different amount of dopants maybe, or the temperature of the crystal is changing as I'm growing it. So the bottom line is that because of the growth process, I have these regions have different properties. So the red region is terminated by the metal contact, and similarly the green region on the right, third region, is also terminated by metal contact. You must have 2 contacts so that the currents can flow. In the middle yellow region, light is shining, right? So this is a problem, and this is an unpassivated surface that simply is giving you a clue that you should consider surface recombination. That might become important. Right? So every statement here is trying to give you a clue of how to make the approximation. So first thing it says, this problem, I'm solving a problem, let's say it's an exam problem, that it is accepted dope. So you immediately in your head you realize that this is essentially all acceptors, and P, the number of holes in the extrinsic region, is equal to Na, right? That's the first thing you immediately realize as soon as you hear the word accepted dope. Now, I said the light has been turned on in the middle section and it reaches a steady state. The right region is full of mid-gap traps. What clue I'm trying to give you here? Full of mid-gap traps means there'll be a lot of Shockley-Rittal recombination, right? Because mid-gap traps are responsible for it. So I have to consider in region 3 in the green part, recombination process, right? Why did that happen? Because when I was growing, let's say for some reason, if I had some unintentional impurities incorporated in the green region, then I may have a lot of traps there. Now, I said the interface trap is on the end on the right side, and the left region, which is red or magenta, that region is trap-free. So I should not have any recombination there. And these are contacted by metal contacts. Okay. Now, you may not realize if you had gone to the talk by Mark Pinto that this is in some simple form an example of a solar cell, in a very simple form. Solar cell has a little bit more complexity, but you get the idea, right? Sunlight striking a section of the solar cell, and the currents are being collected from the outside. So it's a baby solar cell, let's say, because it doesn't have all the junctions and other things. But other than that, let's say we can get started here. How do I solve a problem like this? Okay, the first thing is I'll ask you to recall how we solved the Schrodinger equation, because this is essentially the same procedure. Because at the end of the day, same mathematical equations, you know. So once you have a second order differential equation, whether it's a Schrodinger equation or whether it's a diffusion equation, once it is down on your piece of paper, who cares? It's the same method of solution and same technique. So everything that you have learned there, you will be able to use it here. For example, remember that when you had analytical solutions, we had the second order equation, and in each section, we solved them individually, right? We solved A sine kx plus B cosine kx, or the exponential form. We had these individual solutions in various places. What was the next thing we did? We had the boundary condition on the 2 sides. These are the metal contacts. And this problem, these are metal contacts on 2 sides, and that is sort of the plus infinity minus infinity equivalent to the boundary condition. Then there was all this continuity relationship, right? Do you remember? That allowed us to stitch up the solution from one side to another. We'll do the same here. The 3 regions, 1, 2, and 3, you know, in the last one, we'll stitch up the solution in individual interfaces. And that will give me the global solution. Now, there is no equivalent of 4 and 5, but that's all right. We should be able to get up to 3, and then that should give us the carrier concentration profile. So very quickly, I just want to remind you that this is how we did it. In various regions, we stitch up the solution, applied the boundary condition, and had the whole thing in place. So let me now show you how the brief diffusion equation are solved exactly in the analogous way. We'll see. So we will take one piece at a time. Not all three pieces, one piece at a time, solve it, and then eventually bring them all back together and just stitch it up, or stitch the solution up using boundary condition. Let's talk about region, the middle section, region 1. Little section has light in it, right? Light shining on it, the arrows. So I have that first equation, dn dt. Now I want to make some approximations. What approximation can I make? Think about it and listen to me carefully, because these approximations has a logic which you need to reproduce when you solve problems as well, because I will give you a slightly different problem to solve, of course. This material is acceptor doped, and I have not talked about any variation in doping density. That means the number of dopants is uniform throughout. If it is uniform throughout, that means the P, the whole concentration that is there, that's also uniform throughout. If in equilibrium, before light shining in, if it is uniform throughout, what diffusion gradient do I have? I do not have any diffusion gradient, right? It's uniform. If I do not have any uniform gradient, so you can see the diffusion term must drop. The gradient of n must drop. What about electric field? Does it have any electric field? Well, I haven't applied any voltage here. And the carrier concentration is uniform. So if the electric field comes in from outside, because the carrier, the net charge here, and I'll show you in the last slide, last equation, is also 0. And as a result, no electric field in this material also. Do you see why? Because number of holes, that is positive, right? And the number of acceptors is negative, because they have given those the holes. So therefore, the combination of them has 0 charge. This is charge neutral. Since it is charge neutral, therefore I do not have any electric field. Great, because then my Jn is actually 0. And because it is 0, my big first term goes away on the right hand side of the top equation. Now the n, after light has started shining on it, I can divide it into two pieces, n naught plus delta n. What is n naught? Before light coming in, that's n naught. After light has come in, I have that extra delta n. Where is it coming from? From the valence band. The valence band electrons have jump up, the total amount being delta n. Now, this will assume in the beginning that this is a small injection, light is weak, and so the recombination term, I can write it as minus delta n divided by tau n. Do you remember where this comes from? This was the Shockley-Ridge-Hall recombination in the case of when light, small injection, right? Minority carrier injection. That's where the first term comes in. And the G will remain whatever it is. That's the light coming in. Okay. Now you have seen that I have crossed out the value of n naught. Well, n naught is a constant because remember, this is before light came in. It is uniform. And of course, before light came in, nothing was changing with time. It is only this little delta n that's changing with time. So the n naught is a uniform, time independent. So as soon as you take the first derivative with respect to time, that one goes as well, right? Now you can see that why this equation is very easy to solve. Okay, so that's the first equation for the electrons. What about holes? Holes the same way. Same way, no current, uniform semiconductor, no electric field, and therefore you essentially drop that current also. And in this case, you do exactly the same thing for the holes as well. Now, the electric field one, I could see from some of your faces that you didn't really understand that why I said the electric field to be 0. Now, let me convince you that I didn't pull any trick. Electric field always has to come from the Poisson equation, right? Poisson equation has P minus N plus ND plus and NA minus. I can understand that before I have light turned on, that everything is balanced, charge neutral. Remember, piece of semiconductor sitting by itself, every point the same one. What about after turning the light on? It's still zero. The reason is the delta N, the extra electrons that you have created, is exactly balanced by the extra holes that you have created. As a result, even after shining the light on, in non-equilibrium even, the gradient of the electric field is zero. Now, gradient is zero. That doesn't mean the electric field itself is zero. But remember, I do not have any contacts here. So my input electric field is zero and the gradient is zero. Therefore, throughout, the electric field is zero. Do you realize this? And that's why I was able to drop the term. Okay, now this is a high school equation in a good way, hoping that you'll remember. So you can solve this, right? This one equation I can solve. And you can plug this equation back. This is by integrating factors and other things that you can check. But the one way it is to do it is by simply plugging the solution back in. So I'm solving for the middle region. And if you do that, you can convince yourself that the solution is indeed right. Now I have delta n x sub x comma t. I shouldn't really have to put an x there, right? It's uniform. So I really didn't need that for the time being. But I just wanted to make sure that, that I put the boundary conditions in here. So what are the boundary conditions? At time t equals 0, what is delta n? No light. Delta n is 0 minus 0, right? Delta n is 0 because I haven't started generating any carriers. And so if delta n is 0 at t equals 0, then a plus b must be equal to 0 itself, and a is equal to minus b. You can see. What will happen at t equals infinity after I have shined the light for a long period of time? What will happen? You can see that it will reach a constant. And what is the value of the constant? Is simply a. That is the value of that constant. Okay. Okay, and do you agree with this statement? This at t equals infinity, then things have gotten steady state, right? So that left-hand side of the top equation, what is d delta n dt at t equals infinity? Nothing is changing. So therefore, it must be 0, right? No change. It must be 0. So do you see that delta n at t equals infinity will be equal to g multiplied by tau n from that first equation? Do you see that? That's how I have inserted it in this last equation. So I know the value of A. Do I know the value of B now? Of course, I know the value of B. And so that's my solution. I know everything here. Tau sub n is that is where the number of traps and the velocity, the capture cross section, do you remember? All of those things hide in tau sub n. So if you have lots of traps, it will recombine faster. So that's why the tau sub n sits in. The G is the light that's coming out from outside. And so that's the number somebody will give you, the flux that is coming in. And from here, actually, you can solve the whole problem. So we are already partway there, but let's think about the other two pieces. So this is as a function of time. You realize that it will come in and it will saturate. What is this value? G multiplied by tau sub n. That's the value when things have saturated. Now let's think about the first region. You see what is going to happen, that in the yellow part, light will come in, generate electron-hole pairs, and they are going to get out through the red side and through the green side. They are trying to get out of the device because there is too much carriers. So by diffusion, it will try to get out of the device. So let's think about that. Again, accepted doped. So we know that. Let's see whether we can solve it. Again, the full equation. Now this time, unfortunately, we'll not be able to take out Jn anymore. First of all, can I take out this recombination and generation? Generation I can take out, right? No light. How come I take out the recombination? Because I said trap-free. No traps, no mid-gap levels. Therefore, I can take out the recombination. Okay, that's fine. dn dt, why did I take it out? Because I said steady state. So therefore, that's giving you a clue that I want to know in general how the current flows. So that takes out. Electric field is again 0. I'll explain in a second. But this time the gradient is not 0. Why? Because from one side, from the yellow, carriers are coming in, delta n is not 0. But on the left-hand side in the metal contact, the concentration is 0. And so therefore, there is a concentration gradient. And as a result, we'll have, when you insert the expression for the current into the first equation, do you see that you will have a second order equation for diffusion? You see that? What happened to the Q? The Q cancel, right? Do you see the Q cancel? And therefore, I only have dn and second derivative of n. Now, I'll have to solve that equation in this region 1. And let's assume that that region is A. Whatever A is maybe 200 micron, right? Do you agree with this statement that the solution of this equation is simply a linear solution? That's right? Because second derivative of that must go to 0. So therefore, this must be an equation. Remember, I have said it at x prime, and x prime is going in this direction, going towards left. So I have to just be careful when I put the values for x prime in. Now at x equals a, the delta n is 0. Now this statement I have not explained. I will do that in a second. But let's say it's 0. Now why it is 0 is something that you need to understand very clearly. Why in a metal contact, anytime there is a metal contact, delta n is 0. Why is it? The reason is, once the electrons get out of the semiconductor and gets into the metal, metal has very high mobility. Electrons go very easily, right? When you have a copper wire, put a voltage in it, doesn't a lot of current flow? So electrons have very high mobility and very high velocity within the metal. Now, if it has a very high velocity, in order to support a certain amount of current, how much delta n would you need? It will need a very small amount of delta n, right? Because the velocity is very big. As a result, what will happen that the delta n, because the velocity is very large, delta n is approximately equal to 0. As a result, anytime a semiconductor is contacted by a metal, at that point of contact, I will assume the boundary condition to be equal to 0. It's an approximation, but a very good one. Do you realize this? Okay. So if I have that equal to 0, I can put it in and relate C with D. And I just put x prime equals A. So that's 1. And at x equals 0, delta n will be equal to C. Right? Because I put x prime equals 0, so then I get this. And as a result, if you put those two things in, two boundary conditions in, you get a relationship of delta n varying linearly with distance, something like this. You realize this? Of course, that's the solution. C plus d x prime was the solution, and after I have gotten the value at x prime equals 0, I will have delta n, and it will go linearly to 0. Now, this is something, as soon as you see a trap-free minority carrier, in your head, you should immediately be able to draw this picture, even before solving all these equations. You should solve it many times to get a practice. But trap-free, without recombination, well, you immediately have a straight line going to the metal contact. Now, be careful. If I don't say there's a metal contact there, you should not be immediately be using this boundary condition being able to equal to 0. That you shouldn't use. But it should be always be linear. Anytime it's trap-free. Okay. All right, the last piece. The last piece is full of traps, right? This region. So I cannot do what I was doing before exactly. I do not have any generation, steady state, so I take out delta n, delta t. I get out generation. Why? No light. In that region, no light, so therefore I take out the generation. Now this time, I cannot take out the recombination because this has a lot of mid-gap trap levels. Copper, gold, these are mid-gap trap levels in silicon. So somehow they have gotten incorporated, so I cannot take it out. The electric field is 0, and correspondingly, only thing that is remaining is the diffusion term. So I put it in, put the second equation in the first one, and you can see that that will give me these two terms. The minority carrier recombination, delta n divided by tau n, right? That you remember. Now remember the various approximations we did, that applies in various cases. Had it been high injection, what would have been this value? Delta n divided by tau sub n plus tau sub p. Remember, I was asking that question that how come in high injection the recombination looks smaller? So under appropriate conditions, you will have to replace it with appropriate expressions for recombination, right? If it's direct recombination, you'll put the direct recombination term in, B multiplied by delta n. So whatever it is, as I tell you from the problem, you should be able to pick it up and put it there. Now the N naught, originally before any injection was there, this was a uniformly doped material. As a result, N naught was also a constant and therefore independent of position. As a result, I should be able to take out that N naught because it doesn't have any derivative. And that's my equation. And this equation, once again, I should be able to solve. Do you know the solution of this equation? That's how it looks. Almost like a Schrodinger equation, right? Does it look almost like a solution of the Schrodinger equation? No surprise. Because look, the second derivative, the first term with the second derivative and like the potential term on the next one, they are exactly the same equation. Of course, they should have exactly the same solution. So I have that. L sub n is called a recombination length. This is the square root of dn and tau n. So that's what it is. If you put it in and solve it, I have L sub n I have made it short and written in that form. Again, terminated by metal contact, delta n is 0. And so that relates F with E. And at x equals 0, remember this x and the previous x prime are not the same thing, right? X prime was going the other direction. So with x at the metal contact, it again becomes 0. That allows me to relate E and F. And that's it. That's the solution in here. If you just, there are a bunch of exponential floating around. You put these values of E and F n in the first equation. This is the solution at the end you will get, right? What is the unknown here? Unknown, only thing unknown is delta n. But other than that, do I know L sub n? Of course I do, because I just said it is square root of d dn. Why did I get d? From Einstein's relationship. Because I knew mobility, I measured mobility. Remember all those 4 probe measurements? So I got mobility through Einstein's relationship. I got d, and from d I was able to calculate. And tau sub n, number of traps, the capture cross section, the thermal velocity. From all those things I know, and therefore I can calculate L sub n, and this whole thing is known except this delta n. And delta n I will find by stitching the solutions together in various places. Okay, now do you see it looks like some sort of bridge look in the middle, but look at this is the carrier concentration. In the middle, uniform light shining. So what is the value of delta n in the middle section? G multiplied by tau sub n, right? A certain rate it is being created and it's recombining at the same rate. And so steady state is G tau sub n. And on the left hand side, trap free going to the metal contact, it is getting linearly to 0. So that's one side. The other side is full of traps and therefore it is disappearing faster. And therefore before getting to the contact. By the way, where are those electrons going? They are recombining with the holes. and the holes are being pumped through the contact. So in fact, in the green region, holes will flow in to support the recombination of the electrons. As every electron is moving in, holes will flow in, so that with one extra one, and therefore the current will flow. Because in the circuit, whatever electron gets out from one side, that must be balanced by the whole current from the other side. Okay, now do you see how to calculate delta n? Delta n is already known at x equals 0 and x equals 0 prime. That is the interface between the magenta and the yellow and the green, right? So I put those things in, and that will be equal to g tau sub n. I know everything, right? How do I know A and B? Well, I grew the material. How thick they are, I grew the material, so I know A and B. So in fact, after this, once I know the light, the G, the flux of light, then I can calculate delta n. And as soon as I know delta n, then I can calculate also the current. Because if I know delta n, I can look at the derivative. The derivative of the gradient of that region will give me the current, right? So therefore, I can calculate the current as well. In most cases, what is going to happen is the reverse is going to happen. Let's say you have a little detector you have just built, and the Kobe satellite or some satellite is going out in outer space. You have designed your little semiconductor detector. You put it in the spacecraft, it goes out, and then there is this cosmic showers coming down, right? And in the cosmic shower coming down, and you have on the outside of the device, you have a little ammeter. The ammeter is telling you how much current is flowing. From that, you back calculate what cosmic ray radiation is coming through. You see? So what will happen, Jn is what you're going to measure through the ammeter. And what you are going to infer from it is the rate G at which the flux is coming in, right? And then you can reorient your satellite depending on if it's too much cosmic radiation, then you can take various control action around it. Solar cell panels, you remember these big wings on the satellite they have on Hubble telescope and others, same physics. But over there, of course, you want to catch more sunlight as possible. Again, that is the physics of all this in a simple form. But you see, we didn't solve any complicated differential, partial differential equation. Still, we know so much about these problems. Okay. So, in the last two slides, you have seen that I have neglected the electron concentration, or it's the electric field, and dropped out the drift term, and I have only retained the diffusion term. Now, this is only appropriate for minority carriers. For the majority carriers, I cannot really get out the drift term, and therefore the electric field in that case, I cannot assume it to be zero. So what's happening? You remember that in equilibrium, if it is a homogeneously doped sample, as was the case for the example I just told you about, in that case, the electric field will be zero, because N0 and P0 and Nd plus and Na minus, they will conspire together to make the electric field locally at every point equal to zero. So that was not a problem. Now, remember that this was an accepted doped region, right? That's how we set up the problem. In an accepted doped region, I can say that P0 is equal to Na, right? In equilibrium. In equilibrium, I can say that. Now, in equilibrium, I can also say that the minority carriers, which is the number of electrons, is equal to Ni squared divided by Na in the extrinsic region, right? I'm assuming full ionization, not in the freeze out or intrinsic region. Okay. N0 is a very small number, right? For example, if P0 is 10 to the power 18, and if it is in silicon, what is N0? 100, because Ni squared is 10 to the power 20. And so, N0 is actually a tiny, tiny number. Fine, but it is flat, uniformly doped, and together they make the electric field zero. But you remember, for the problem that we are solving, the carrier concentration in non-equilibrium case was not 0. And then what will happen to the electric field? That's what I want to explain. So you remember that there were, in the middle section, light was shining. It generated electron-hole pairs, G multiplied by tau sub n. That was the extra carriers. And it was sort of coming out in region 1 and region 2 contact sites. It was coming out. And let me assume that it was coming out with some sort of, in the trap-free region, with a linear profile. There, my carrier concentration is no longer n naught. It is a little bit more than that, delta n, right? Now, in principle, then I cannot neglect the electric field, because I have a delta n, but it is not a photo-generated region, so I do not have a corresponding delta p here. As a result, how come my electric field be equal to 0? That's the problem, right? That's the problem. That is the part I didn't explain as clearly. Now, what is going to happen is, because in any system, the system wants to minimize the electric field, because the energy goes as E squared, the electric field squared, at every point. So it always tries to minimize the total amount of charge on the right-hand side. So what's going to do as a result, that it will pull in, it will increase the electric field a little bit in that region, a little bit, very tiny amount, and it will pull in holes from the contacts to exactly, almost exactly compensate the electron concentration. So it's not photo-generated. It is coming in order, because it wants to minimize that quantity on the right-hand side. So it will pull in a little bit of holes to sort of match the profile. Now, do you see here that this region is almost charge neutral at every point, almost, but it's not density neutral at every point. The density is no longer the same, right? At every point, density is non-uniform, but charge-wise, it's essentially more or less the same. And as a result, that delta P flowing in from the contact, this is almost equal to 0. Now, why couldn't it make delta n exactly equal to delta P? Well, if delta n is exactly equal to delta P, then you don't have any electric field. And if you don't have any electric field, then the holes cannot come in, right? In order to make the holes flow in, you will have to have an electric field. And if you do a calculation, this electric field will be on the order of a microvolt. As a result, for minority carriers, I was able to get rid of the electric field term. However, for the majority carriers, 10 to the power 18 sitting in the first term for the number of holes, a tiny electric field can still have a huge effect. So drift is not negligible for majority carrier, drift is only negligible for minority carriers. That is how this thing works out. Now, actually, if you have done the homework, you already know this, because you have already seen this electron and hole exactly balancing each other in your plots. But you may not have realized it, but when I return the homework, then you should double check and see whether you agree with the statements that I just made in terms of understanding why you can neglect the electric field. Okay? So let me conclude here. What I began discussing today is the continuity equation is a basis for semiconductor device analysis, because this was like a capstone for all the 5 equations that you needed to think about. These are actually done. And this is generally, continuity equation is always true. You should be able to take any device, any problem, and without consulting any textbook or anything, be able to write the continuity equation, be it for phonons, photons, electrons, whatever it is, you can write it. The full numerical solutions are possible, and I will cover it in the next class, a discussion in the next class. There are commercial simulators that you can buy with $100,000 that people, and when I was in Bell Labs and also at Aegir Systems, I have used this a lot. These are like 80,000, 90,000 lines of code. solving those 5 equations of a variety of situations. But that doesn't give insight. So being able to solve a complicated problem in a computer, well, computer knows more than you do, most of the cases, and you cannot catch your mistakes. Then let's say you put a wrong value of tau sub n. You wanted to write 10 to the power minus 5. Instead, you accidentally wrote 10 to the power minus 15. Well, computer will give you some answer. But if you don't understand the analytical way, that what the result should be, then the computer will give you a completely ridiculous result. You will take it to your boss and will get fired. And the final one is, no, I'm not saying from personal experience. Now, and the final one is analytical solutions provide a great deal of insight, and this is something requires years to develop. But once you develop it, this becomes powerful. You almost, without solving the equation, the solution floats to you. You can just look at the problem and you know what the solution is going to be, without solving any problem on a long derivation or simulation. Okay? All right, that's it. Thanks.